the reliability of this kind of estimation of proxy yield map, considering the fact that we're going to be taking these images a month, maybe 2 months ahead of harvest. Are they any good? Well, it's probably of no surprise to you that the value of these depend on the weather. Weather probably has 25% or more to do with the last amount of grain produced as anything else. Weather is very important. Water is key. But also, there's a lot of differences between fields. Perhaps it's because of different hybrids, the previous cropping systems are different, fertility practices. So a proxy map and the procedure you use on your field will be different than on the neighbor's field. And then you can expect the yields to change from year to year because of a whole bunch of different factors. So you say, well, my gosh, this isn't even worth it. But I think there's a way around this. And the approach that we're proposing here is to talk about normalizing the data. And what that does is it takes out the specifics of each individual field, and it lets us compare now across years, across hybrids, and start to get a bigger picture of what's going on. Well, what is normalization? I'm going to tell you now, it's nothing new, but it's a big word. And it amounts to referencing your observations to some kind of a standard. That standard is unique to your field, your situation. Now, in some situations, if you have a research plot study, you might say, well, I'd like to reference everything to the highest yield in my plots or my study. In the case of SPAD meters, we would typically use the highest nitrogen rate as our reference. And likewise with fertilizer, we might use the highest fertilizer rate, assuming that that will apply more than enough nitrogen for the crop. And so the readings that we get from our sensors or the imagery from that high nitrogen rate, that's going to be the happy crop. In other situations, it might be more appropriate to use only the mean value for the field, the average yield perhaps, as our reference, and go 20 or 30% either side of that. And then in the case of crop canopy sensors, many times they will use either a nitrogen-rich strip through the field, or there's a new technique called virtual reference strip, whereby it selectively uses data from the most vigorous plants within the field as that reference. So that's what we're going to compare to, is the healthiest and happiest plants. I told you that this reference or standard is nothing unique, but it is unique for your field, your year, your hybrid, your growth stage, because we're dealing with a biological system that is changing all the time. So that's why it's going to be important to normalize the information. As an example, we've been normalizing information for a long, long time. We talk about percent. The denominator is 100, be it pennies, pesos, or whatever. So that's the idea behind normalizing. It really wasn't used very much in agronomy and agronomic services or ideas until about 1990, when the chlorophyll meters came out. And in those cases, we had to figure out a way to be able to talk about changes in chlorophyll meter readings between different growth stages different fields, different hybrids. And so it sort of became obvious that this high nitrogen rate would be a good reference. You've already seen this many times, but it's important to caution you a little bit. And we've sort of done that already, but I've listed here the fact that these vegetation indices or sensor readings, they're going to change. You've got this biological system that has different growth stages. The leaves behave differently. They follow the sun or not. There's cultivar differences. The previous crop, whether it's a legume or summer fallow or a crop that has lots of residue like corn after corn, those all make a difference. And then you put on top of that water stress. Whenever you have water stress, it will affect the near-infrared reading of the crop much sooner than it will the visible. The crops tend to protect themselves by reducing transpiration, and that really reflects changes in the biomass, the way the sensor sees the biomass. So you have to be very careful if the plants are under water stress. And finally, soil properties, perhaps like salinity, can indirectly impose other kinds of stresses on the plant. So always be careful. Ask questions. So the theory behind these proxy yield maps then is to think about how can we predict a relative yield based on in-season information. Some people like to have a hard number when they talk about yield. I want it to be so many kilos per hectare, bushels per acre, and so they want a cold hard number, and yet when we're talking about predicting things a month down the road or 2 months down the road, and we've got all these other factors that can possibly change the values that we're seeing, what we've come to realize is that it's really important to normalize this information first. And I show you one example here of how relative crop vigor, and we called it sufficiency index here in this case, how relative crop vigor is related to relative yield. In this case, this was information collected on 2 different growth stages, at the 9-leaf stage and again at the 12-leaf stage. What we find is that it's almost linear. There's great linearity between what that plant sees in terms of vigor and what the yield is going to be. This is why we feel comfortable talking about relative values. We can go from one field to the next, one hybrid to the next, and they're going to respond quite similarly. I'll give you an example here of what normalization really amounts to. I show you a typical nitrogen yield response function. At the highest nitrogen rate, I'm going to call that a happy crop. It's, I'll say, reached a plateau yield. Might be nice to have one higher yield level or fertilizer level to document that, but nonetheless, we're going to call that the happy crop. If we normalize the yield now, we no longer have megagrams per hectare. We now have percent. So we have 100% or 1.0 relative yield, and the shape of the curve is very similar. It's the same. It's the same data, but now we can talk and compare across yields, fields, years, those kind of things. This is a bit of review, but Now the information that we're hoping to get from this imagery, and the only way we're going to get the infrared or near infrared waveband is to go to color infrared imagery. And so we're going to get a green band, and that tells us a lot about the chlorophyll, and it links back to nitrogen. Now the red band, remember the red light is being absorbed during the photosynthesis process, so we probably aren't going to see a lot of red light coming back. And in fact, that's why we don't see many red plants in the field or blue plants. Those plants and its chlorophyll process, photosynthesis, is absorbing all that blue light and the red light. So what we've got to work with and what our eyes capture is the degree of greenness. And finally, we've got near infrared. We said that's the living biomass detector. That tells us how big the factory is. The red light tells us how fast it can work. So that's why we put these two together in a vegetation index. A little picture here of what we're really talking about. I've tried to assign some colors of what might be the leaves in these different kinds of plants. But the important thing is that our sensors and the imagery, they're very sensitive until we get to the point of having luxury consumption. Corn plants are notorious for taking up more nitrogen than they can use. And when they do that, something else becomes limiting. Something else reduces the ability or limits the ability of the plant to produce more metabolites. And so the yield tends to reach a plateau. And the sensors and the imagery are not able to tell us how much extra nitrogen is in that plant. This is where we have to go to tissue testing.